So you were asked what the heck this arch was for. Out of the many guesses we received, 2 were correct, and they were spaced very closely together. The first correct one came from Dominic Bosco, so attaboy, Dominic. Before we dive into this, our goal is to provide a relatively simple description of a very complicated system. This means that we have chosen to disregard a number of fine points such as the effects of temperature and salinity on the density of water. Even though an engineer may be able to pick this apart, keep in mind that most folks aren't really interested in extreme detail, just a general idea of how it worked. The arch was part of a device called a balancer that in turn was part of the hydraulic gasoline fueling system installed in 1925 for the aircraft. The balancer's function was to correct for differences in fuel density made necessary by the way the system worked. This was an extremely clever system that used the weight of water to push gasoline through pipes from tanks located close to the ship's bow to an outlet beside Turret 3 where it was used to fuel aircraft. It took advantage of 2 basic characteristics of gasoline and water. First, gas and water do not mix, and second, water is heavier than gasoline. While the system and its piping was very complicated, its operating principle was quite simple. Gasoline is stored in tanks close to the bottom of the ship. Any empty space in the tanks is filled with water that also fills all of the pipes above the tanks. At the top of the system was a measuring tank. If you wanted to pump 100 gallons of gas, you put 100 gallons of water into the measuring tank. You then open valves and the weight of the water pushed through the pipes into the bottom of the gas storage tanks where it would push the gas up and out through supply lines. Why go to this effort when it would be easy to take a very safe pump and simply suck the fuel out? Gasoline was almost certainly the most dangerous substance stored on the ship. It's far more flammable than fuel oil, and its vapors are extremely explosive. This system kept the tanks and pipes either full of gas or water or both to eliminate empty spaces where explosive vapors could form. For ultimate safety and when setting for battle conditions, they would drain the long fuel line that ran outside of the hull and pump water backwards through the pipes to clear them and push gasoline back into the 12 cylindrical storage tanks. The tanks would then be closed off to isolate the gasoline and protect the ship. A final protective step was taken. The 12 tanks were located in what was originally a forward trimming tank. Prior to going into action, they flooded that compartment so that the gas tanks were completely immersed in seawater, eliminating the possibility of a gasoline explosion or fire if a tank or a fuel line was ruptured. So what about the arch and balancer? What did they do? As we said before, gasoline and water will not mix. Since gas is less dense, it will float on top of water. The density of gas also varies by grade or octane rating and manufacturing variations. So there has to be a way to adjust the system to correct for changes in gasoline density. Here's the basic problem. Let's say that you want 100 gallons of gas, so you use 100 gallons of water to push gas out of its storage tank and through a pipe. What you are doing is using 835 pounds of water to push against the fuel. A little math work tells us that the resulting 835 pounds of gasoline measures out to about 133 gallons, so you end up with 33 gallons more than you want. So in order to set 100 gallons of water so that it will deliver 100 gallons of gasoline, the amount of water has to be reduced by a measurable amount. Here is a drawing of the balancer quadrant or arch that we've been guessing about. The red circles accent one of its rows of holes. Even though they are unevenly spaced on the arch, notice that horizontal lines extending from each hole are perfectly spaced apart at 5 and 11/32 of an inch. This is the key to what happens next. The actual balancer is made from a pipe shaped like an inverted U and mounted on swivels that allow it to rotate. Unwanted water could be drained through it to reduce the amount of water used to push against the gasoline. By swiveling to adjust the tilt or height of the loop, it increases or decreases the amount of water in the system, meaning that it can be used to correct for changes in gasoline density and deliver the desired amount of gasoline. Since a decrease in specific gravity of gas increases the amount of it you end up pumping, you need to set the angle of the balancer to a lower angle to drain off more water. The numbers on the side of the arch allows you to set the balancer for the exact density of the gas being pumped. Here we can see the difference in the loop's height when it is set for 0.78 and then again at 0.71. Think of them as two different settings for a dam spillway. You can see that changing from one to the other will clearly change the amount of water allowed to drain out of the system. In this slide, the balancer has been set at 0.78. It drains off enough of the initial 100 gallons of water to reduce the gasoline delivered to the desired amount of 100 gallons. The balancer has now been rotated down to a setting of 0.71 for a lower grade, lower density of gasoline. The effect is even more water will be drained, and what would have been a greater amount of gasoline delivered will now be limited to 100 gallons. The system was extensively modified prior to World War II. While we haven't seen any documentation that tells us why it happened, a couple of reasons come to mind. As a gravity feed system, it would be impossible to pump gas to a level above the balance tank. This would include something like the wing tank of an airplane sitting on top of turret 3. It is also likely that it pumped at a fairly slow rate. The original solution prior to the modification was likely a portable booster pump at the turret end, but there were risks involved with that. Beginning sometime around 1940, the measuring tank was removed and a booster pump was installed. A booster pump could deliver fuel faster and could pump it anywhere it was needed, plus its addition did not compromise system safety. The pump itself was inherently safe because it operated using pressurized seawater from the fire main instead of electricity or steam. The pipes and valves needed to drain lines and purge them with seawater continued to be used, and the gas storage tanks were still filled with seawater as they emptied. So while the original system was rendered obsolete by increasing demands, that does not remove the fact that it was a very clever design that met its original design goals, was incredibly flexible, and most importantly, was very safe.